In this video, we're going to see Einstein relation in semiconductors. Einstein relation is between the quantities diffusion coefficient to that of mobility. And we have diffusion coefficient for electron and mobility for electron, and diffusion coefficient for hole and mobility for hole. Einstein relationship talks about the relationship between dn and mu n, dp and mu p. So to understand this, first of all, let's see how we defined the diffusion coefficient and mobility, where we saw the Jn drift was given by Q times N times mu N times the electric field, where we have seen that the drift velocity of electron is actually given by, if you take in vectors, it is actually minus mu N times electric field. Minus indicates that the velocity of electron is in the opposite direction to that of the electric field. We defined mu n as the proportionality constant, which we call as mobility of electrons. Let's say for a given electric field, if you have different values of mu n, where if mu n is higher, the velocity would be higher, and mu n is smaller, velocity would be smaller, which means mu n basically tells us the ease with which the electrons move in the semiconductor under the influence of electric field. And now let's look at the diffusion current that we defined, which was equal to Q times dN times del N by del X, where dN was the proportionality constant we defined, which is called the diffusion constant or diffusion coefficient of electrons. For a given concentration gradient, which is del N by del X, if you take different values of dN, if dN is smaller, then the current that we get would be smaller, because the rate at which the carriers flow depends on dN under no applied electric field, only because of carrier concentration gradient. And if dN is smaller, the diffusion current would be smaller, which means dN basically tells us the ease with which the electrons move inside the semiconductor under no influence of electric field, just the concentration gradient. If you see the two quantities mu n and dn, both of them talk about the ease with which the electron moves inside the semiconductor, but one talks about under the influence of electric field, and the other one talks about when there is no electric field, only concentration gradient. And as both of them have one thing in common, that the ease with which the electron moves in the semiconductor. Let me take a semiconductor in which we are talking about the diffusion current and drift current. Then we are pretty much talking about the ease with which electrons move under electric field, one quantity, and under no electric field, another quantity. Both of them are talking about the same carriers, which means there should be some relationship between these two quantities. And that's what is given by Einstein's relationship. This relationship says that dN is actually given by kT over Q times mu n, and dP is given by kT over Q times mu p. The units of mobility are given by centimeter square per volt second, and diffusion coefficient units are centimeter square per second. We saw these units when we defined those quantities. Looking at this, we can say the units of kT over Q should be volts, so that volt get cancelled and the units on left side will be equal to right side. So kT by Q units is basically voltage, which is potential. And we have a notation which we call a V suffix T to this. So whenever we have kT over Q, we'll write as V suffix T, which we call as thermal voltage, because this depends only on the temperature and rest of the things are constants, where K is a constant, Q is a constant. And this voltage depends only on the temperature. So we call this thermal voltage. And at room temperature, where T is 300 Kelvin, then Vt is equal to 25.85 millivolts. And approximately it can be written as 26 millivolts. Now we're going to derive and prove this relation. If you're not interested in the derivation, you can stop watching the video at this point. To prove this relationship, we need both the currents, the diffusion and drift currents, to be present in the semiconductor. So in order to have that, I'm taking this piece of semiconductor and I'm going to dope it with pentavalent atoms. so that this semiconductor would become n-type. And let's say the doping concentration we are adding is in this way. It is changing with respect to distance. So let me call this ND, the doping concentration with respect to distance. If I hypothetically assume that the electron concentration to start with is also like this. At this point, the energy band diagram would look something like this. Electron concentration of this n-type semiconductor would be higher at the left side of it, and at right side it will be lower. To represent that, we know EF minus EI basically represents the electron concentration. So it is higher on left side and lower on right side. So this is our Fermi energy level, where this is closer to EC at left side and far away from EC on right side. But still throughout it is n-type. Now if we allow the time to proceed, there would be a concentration gradient which would trigger a diffusion current, which means the electrons on left side here, let's say at side A, would be higher compared to the electron concentration at B. So these electrons would move in this direction. So as a result, we'll have a diffusion current, which we call Jn diffusion, will be in this direction. Because the electrons are flowing now, here on A side, the electron concentration would decrease, which would result in exposing the donor dopants, which would be ions now. So we have a positive ions present on left side. And because we have electrons in excess went to the right side compared to the doping, so we have relatively negative ions there. So as a result of this charge present, positive and negative, we will have electric field established. Because of this electric field established, now electrons will be moving from this side to this side. As a result, we'll have current, and this current is drift current because it is influenced by the presence of electric field. And this drift current would be in the opposite direction, which means it would be in this direction. So this let me call as Jn drift. But if you see, we haven't applied any potential across this n-type semiconductor, which means there should not be any net current flow through this semiconductor, which means the Jn drift plus the Jn diffusion should be equal to 0. So now let me put that equation. Before we do that, let us see how this energy band diagram would get modified once it reaches the equilibrium. Now this band diagram would get modified in such a way that the Fermi energy level throughout the semiconductor should be constant, because we are saying there is no net current flow through this n-type semiconductor, in which case EF will be constant. So I'm taking EF to be constant. If EF is constant, then basically EI would have a relationship like this approximately, and then EV would be parallel to this, and EC would be again parallel to this. Now let us put this equation to test, that Jn drift plus the Jn diffusion should be equal to 0, because the net current should be 0. Now if you write the expression for this, Jn drift is Qn mu n times electric field plus Jn diffusion, which is Q times dn del n by del x. Now the question is, what is the electric field and what is n? And for sure we know what is n, which is given by Ni times e power Ef minus Ei over kT. So we can write that del n over del x would be equal to, now in this case we can see Ef is not changing with respect to distance, which means Ef is not actually a function of x, but Ei is changing with respect to x, the distance. So Ei is actually a function of x. So now let me write this. It would be equal to Ni times e power Ef minus Ei over kT times del Ef over del x minus del Ei over del x times 1 over kT. Now this del n by del x can be written as, this whole thing is nothing but n times, we know dEf over dx is 0. So this would become minus n times del Ei over del x times 1 by kT. I'm writing it here. So this is del n over del x. Now what is electric field? Now we can write electric field E as 1 over Q times del EI over del X. And EI is changing with respect to X. And we will see why we can write electric field in this way in next video. So now let me take these two equations and let me substitute in this equation so that we can write this as Q times N mu N times 1 over Q times del EI over del X. This quantity is nothing but the electric field, plus Q times dN times del N by del X, which is nothing but minus N over KT times del EI over del X. This should be equal to 0. Now we can reduce this to N mu N times del EI over del X minus Q over KT times dN times N times del EI by del X. This is equal to 0. Now we can take N times del EI over del X common in this equation, which can be written as mu N minus Q over KT times dN. This should be equal to 0. We know that N is not 0 because there is electron concentration in the semiconductor, and di by dx is also not 0 because we know EI is changing with respect to distance. And the only quantity that can be 0 is this. So we can write mu N as Q over KT times dN. And I can rewrite this as dN is equal to KT by Q times mu N. So this is the expression which is called Einstein relation between diffusion constant and mobility. In the similar lines, we can prove that dP would be equal to KT over Q times mu P.